Next up, it's my pleasure to introduce Daniel, who from Edge Impulse, where he's a founding tinyML engineer. He's a technical leader in the field of embedded machine learning. He authored the field's leading textbook on tinyML and sits on the organizing committee of an international network of over 4,000 embedded machine learning engineers now. He currently heads the tinyML R&D at Edge Impulse, which is a leading startup in the field. And he was previously a lead developer at Google. So again, without further ado, I hand it over to Daniel now from Edge Impulse.
Hi, everybody. Thank you very much, Stephen. I'm excited to be speaking to you all today. So let me share my screen. This is always the scary part. We'll see if this works. Okay, do you see the slide all full screen? And
yeah, looks good.
Okay, fantastic. All right, so today I wanted to talk a little bit about embedded ML as it translates to the real world. So there's a lot of information out there about the state-of-the-art results that researchers are getting and the type of work that's happening as we look into the future of ML at a tiny scale. But what often gets neglected is what does this stuff look like as an engineer today? So if you're building an embedded product as an embedded engineer, as opposed to being an ML researcher, what do you need to think about, and what are the things that you can do fairly easily now, as opposed to things that are going to be possible in a couple of years? So just to introduce myself briefly, I'm a lead engineer working on tinyML at Edge Impulse, which is a really cool company where we're basically trying to take all of this amazing stuff that is being done by the ML research community and make it available to embedded engineers in a way that fits into their workflow. Prior to that, I wrote the tinyML book by O'Reilly, which is another kind of engineering manual for engineers to learn about embedded machine learning, with Pete Warden there. And prior to that, I worked at Google on the TensorFlow team. And prior to that, I did this crazy thing where I started a agricultural technology company. And that was the sort of place where I first got a taste of working with embedded sensor data in a context where ML made sense. So I've sort of been thinking about this stuff for quite a while. And over the next 15 minutes, I wanted to basically go over just a few things. So first of all, a quick intro to what is special about embedded ML from an engineering point of view. What are the magic powers it gives you as an embedded engineer? I wanted to cover some of the real world use cases that unlocks, because I think that's where this stuff gets really exciting. And then I want to talk a bit about the state of the art for practical deployment. So rather than talking about like what is possible with the latest advances in algorithm design or the latest types of techniques that we have for building ML models, I want to talk about what is the state of the art for stuff that an engineer can do practically without having to do a huge amount of kind of original work or background reading to understand what's going on. And then I want to talk about the big opportunities in the space. And this is sort of about the difference between what is possible now if you're a researcher and what is possible now if you are an engineer who's not an ML person. And I want to talk about what the future is going to hold. So to just give a very kind of basic introduction, from an engineering point of view, this is what embedded ML looks like. So you train machine learning models using data science tools. And these are often the same tools that you might use if you were doing analysis of a data set to figure out what a price of a house is going to be in your neighborhood 5 years from now. They're the same battle-tested data science and statistical tools that people have been using for years. But the twist is you then deploy the model that you've created to cheap, low-power microcontrollers. And this is where this gets exciting, because this is the stuff that hasn't really been possible until quite recently. And the third part is that on the microcontroller, you are running inference. Usually when we talk about embedded ML, we're actually talking about embedded ML inference rather than training. And the training happens in an earlier step. So on the device, we are running inference to analyze sensor data close to where it comes from. So that's the important thing. Like the benefits and the rewards we're going to get from doing this come from the fact that we're analyzing data right where it's produced. So I'll talk a little bit more about the reasons why that's cool. So I really love this acronym BLURB, and this was come up by Jeff Beer, and it stands for bandwidth, latency, economics, reliability, and privacy. And these are the things that are unlocked for you by doing machine learning on the edge. So this is wherever you're doing machine learning inference, close to where the data is being produced. So I'm going to walk through these quickly. So in terms of bandwidth, so algorithms that are running on edge devices can extract meaningful information from data that you wouldn't otherwise be able to get off the device. So it's pretty common if you think about like an IoT deployment, you might have sensors in a place that doesn't have good connectivity. So where you might have the ability to capture an image, you may not have the bandwidth to transmit that image off the device. And until recently, there's only limited sort of stuff you could do with an image trapped on a microcontroller. So luckily now that we've got embedded machine learning, you can have these like sort of anything that takes up a lot of memory or is super high frequency or otherwise would consume a lot of bandwidth to transmit. We can analyze that close to where it's produced, and we can learn something from that and then transmit what we've learned instead of having to transmit raw data. The next thing is latency. So this is very closely coupled to connectivity, but there are some places where even if you had amazing connectivity, you're not going to trust your workload to an internet connection. So one example of that would be in autonomous vehicles. It would be horrible to think that if your internet connection goes down, your car suddenly loses the ability to steer. So this is another really important reason to push computation onto devices, because you get less time it takes between your sensor data coming in and a decision and a reaction happening. And so you're less vulnerable to problems on the network. And there are some places where you just need real-time decision-making, like driving a car. Economics is also super important. So transmitting data is often the most expensive part of the ongoing costs of running an IoT deployment, in addition to a big part of the bill of materials if you need to spend money on a big modem that's going to be sending data. So if we can avoid transmitting data and avoid the cost of processing it on a back end, we can save a lot of money. And the other thing worth mentioning there is like tinyML is super cool because we can run really tiny models on device. We don't need super capable, super expensive devices to do it. Reliability, I mentioned a little bit that earlier with regards to the self-driving car type stuff. If you're dependent on a cloud connection, you are not going to be able to operate in certain places where that's not available, and you're also vulnerable to the connection going down. So on-device models are inherently more reliable. And in terms of privacy, if you're processing data on an embedded system, this is actually my favorite part of this acronym. I think it's the most important one, because when data is processed on an embedded system, it is never transmitted to the cloud. You can learn from the data, you can understand what's going on, while potentially still guaranteeing the privacy of the person or the community that is using that application. So that unlocks so much if you think about deployments of artificial intelligence and machine learning within workplaces, homes, medical settings, anywhere where you might be concerned about the data leaving the device. And this can be important in industrial applications too, because for example, in the agricultural technology work I did, a lot of farmers are very conscious about sharing their data with third parties. So if you can do processing on a device and understand what's going on device, you can give people what they want, which is for their information to stay theirs. So having talked about these, I want to go over some real world use cases that they unlock. So in an industrial setting, so anything from equipment monitoring to predictive maintenance or asset tracking, there's so much that's happening in any given industrial context that being able to understand what's happening down on the device at the level of an individual shipping container or pallet, or inside of a machine which you're monitoring for wear and tear, can save a huge amount of time and money. And it's basically, if you're able to do that on device, you can do things in a way that wouldn't be feasible if you had to send people out to inspect stuff. Ag tech is a cool example of this, just an industry vertical where there are tons of applications. So whether that's crop health monitoring, attaching sensors to monitors that are out in fields in places where there's not good connectivity, but still being able to get some insight into how plants are doing, through to things like controlling equipment or making sure that food safety is maintained through a cold chain supply chain. Automotive, so I mean, self-driving cars is the kind of big crazy one, but just things like unlocking new types of sensors, like radar sensors, where it's high bandwidth data, where it's difficult to do anything with that unless you can do some analysis close to the sensor. Safety monitoring, figuring out what's going on in a vehicle. Has it crashed? Has something gone wrong? Controlling the powertrain of a vehicle, optimizing what's going on inside of a powertrain while the vehicle's in motion. Wearables is a huge one. So that's everything from fitness monitors like the watch you wear when you're going for a run, through to the types of technology that people with health conditions make use of to enable them to do things that they otherwise wouldn't be able to. And then things that are useful for personal safety. So can you monitor whether a worker has been exposed to unsafe conditions, or whether something that's happened that is important from a workplace safety perspective. Consumer electronics also super important. So everything from device personalization. So imagine if your toaster can recognize that it's you standing in front of it and not your partner, and it automatically does the correct level of brown for your toast. Through to having smart home devices that are privacy aware. So there's obviously a lot of consumer fear about things like having Wi-Fi connected cameras in the home. Maybe your baby monitor is connected to the internet, and it would be kind of nice if you can get a message that says your baby is crying without having to have audio from your home streamed to some insecure, potentially insecure cloud server. And then going all the way through to ambient computing, which I think this is what we're going to see more of in the coming decades, is basically everything in our built environment will have some degree of intelligence and ability to understand what's going on around it, so it can do a better job of smoothing the rough edges of human interaction with our environments. And sustainability, which is something that we really care a lot about at Edge Impulse, and has actually been kind of an amazing thing for embedded ML. We've seen so many organizations who are starting to deploy this technology, doing everything from monitoring animal behavior through to measuring whether people who work with nature, so for example, fishermen, are complying with regulations. And generally things that help humans live alongside nature. So one of the projects we've assisted with is called Elephant Edge. And they're basically using embedded ML and sensors to understand when elephants are straying into places where there are human settlements, so that people can be warned. So it reduces the risks associated with conflict between wildlife and people. So having gone over a few of these exciting use cases, and there are tons more that I don't have time to cover and that I'm maybe not even aware of, I want to talk about the practical state of the art for if you want to deploy this stuff in 2020. So the important thing for me is that what we need to do as a field, if we're thinking about sensors and ML, is make sure that people who have domain expertise can use these tools. That's what's really, really important to me, is not that I can do all this stuff and I have a great understanding of machine learning and I can train a model on any data set, but that people who actually have practical knowledge about what types of data are available, what kinds of sensors are important, what the problems that need solving in all of these tightly scoped domains, from ag tech through to astronomy, are all able to have access to the same tools that we do as ML professionals, in order to build solutions, because they're the ones who actually know what they're talking about. We can just approximate some domain knowledge after doing some research, but the people who actually have their hands dirty in the field need to be able to use the tools that ML researchers are creating. So what we have today, what people can easily access as researchers, are tiny models, first of all. So we have model architectures that work with all the sensor types that you're likely to see in the field, whether that's time series of any sort, image data. There are model architectures that have been proven to work with all of these, and that have been shrunk down to the type of scale that will fit on the typical embedded or edge device. We've also got some pretty mature digital signal processing pipelines that pair well with these models. For example, if you're going to do some audio analysis, there are all sorts of techniques with FFT or MFCC type algorithms that can help you transform raw audio into a form that's easier for a tiny model to understand. And there's obviously room to improve things in those pipelines, but we do have the tooling to basically get raw sensor data into a model. And we have tools to do basic model optimization. So for example, with the TensorFlow Lite tooling, or with Edge Impulse, the product that my company develops, we have the ability to do intake quantization. It's super easy. This is something that a few years ago would have been out of reach for most people. Today, it's within reach of the average embedded engineer. We also have accelerated hardware to some degree. So there's a lot of silicon that has digital signal processing, or at least SIMD capabilities, which can help out a lot with signal processing and ML workloads. So an example of that would be ARM SimSys libraries, which make use of the ARM hardware in the best possible way for running DSP and NN tasks. There are also some ultra low power MCUs which can do the same stuff. So for example, Etacompute has built some really cool hardware which is designed for this sort of strange workloads that embedded ML sees, where you're going to be doing nothing most of the time, and then occasionally you wake up and do some pretty intense math, more than what you'd usually do in an MCU, and then you go to sleep again for a while. So how do you make sure you're using the least energy throughout that process? And so also on the horizon, these are just starting to become available, are the types of purpose-built accelerators for deep learning models. So for example, Sentient produces neural network accelerators for specific purposes, and these types of things are starting to become more and more available, and the tooling is becoming available to help you target them. So this is a really important piece of the puzzle, because as an average engineer, you can't go and learn to do all these different things. You can't learn to optimize models, train amazing models, write low-level code to run the models, making the use of all of the right libraries for your particular target platform. Even collecting data can be a challenge. So there are a few companies, including ours, that are building end-to-end tooling for this whole thing. So it starts with ingesting data, grabbing data from sensors to form your training set, because data is always a big problem, and then managing that data. And then it comes through to model training, also ML and architecture search that doesn't involve writing code and doesn't involve knowing how to use these low-level Python tools that ML engineers are used to. And then keeping track of versions of models over time as you improve them. And then the other big thing is deployment. So when it comes to, okay, I've got a model, I have a DSP pipeline to go with it, how do I deploy this to all sorts of different targets that have completely different capabilities and are good at different types of things? And how do I get an understanding for how this will perform before I deploy it to the target? So products like ours basically allow you as an engineer to just do what you do best, focus on the problem domain that you understand, and then use a fairly straightforward workflow to get the right data, train and validate a model, make sure it works well, and then deploy it on device in a way that runs efficiently. So that said, there's still a lot of opportunity in this space. And as people who have some knowledge in the intersection between sensors and ML, there's huge opportunity here to build cool new tools. So some of these opportunities are software support for the state-of-the-art optimizations that we see in the model arena. So for example, pruning is something which it's now fairly easy to do during training. So to prune a model, to end up with a sparse model which has a lot of zeros in the weights, it's relatively straightforward. But there isn't good software support for actually running a pruned model and deriving any benefit from it whatsoever. So there's a big opportunity there to create some infrastructure for running sparse models efficiently. Same with lots of the optimization stuff. For example, binary neural networks, where you're quantizing all the way down so each weight is a single bit. That's a proven technology. Those things work, and they can work really well, but there aren't really any frameworks or any sets of tools that allow the average embedded engineer to train a BNN and deploy it to a typical device. So these are proven in the science, but the engineering hasn't landed yet. Another big thing is embedded specific deep learning architectures. So in the previous talk, we saw how with neural architecture search, you can find an architecture that works well on a particular embedded architecture. But this is also something that's not very well flushed out. I mean, if you look at the work that most ML researchers are doing in terms of trying to attain state-of-the-art results, they're looking at what is the high end, what can you do with as big a model as you can possibly get. And there isn't that much competition on the low end, like how much can you squeeze out of 250 kilobytes or even 10 kilobytes in a model. Another big thing is the smarter division of embedded DSP and ML workloads. So how do you split up the work so that you're minimizing memory use? How do you split up work so that you're running maybe the DSP stuff at the most appropriate time given the duty cycle of the MCU that you're running on and its capabilities? And how do you split workload across co-processors and things like that? And then finally, we're really lacking public and commercial data sets for industrial use cases around sensor data. There's really a dearth of data out there that can be used for researchers and practitioners to experiment in coming up with these types of things. So I think there's some huge opportunities here to like build some amazing tools and write some fantastic papers that meet some of these needs. So finally, I want to talk about what's going to happen in this space if we fast forward 5 years. So we know what things look like today. It's actually, I think we've just finally in the last few months passed the threshold where the average embedded engineer can really work confidently with deep learning, with machine learning generally. So what's this going to look like in 5 years' time? So I think embedded ML and ML alongside sensors is really going to be this transformative technology that I think that the wider world doesn't quite appreciate yet. I think this is one of the things that's going to be painted as kind of a dark horse that came out of nowhere. No one was expecting it, and this technology transformed the world. Whereas for those of us who've been working in it for a while, we can kind of see it coming. But I think the types of products that are unlocked by embedded ML are going to be in incredible demand by both industry and consumers. I think this is going to be the main type of workload that people run on embedded devices because of that demand. I think once people start seeing the type of experiences that consumer products can deliver, or the types of savings and efficiency and safety improvements that industry sees, this is going to be absolutely massive. So we're going to see most MCU architectures have some kind of support for machine learning, deep learning, or at least DSP that's geared towards that to unlock the use of this type of technology with those devices. And I think nearly all embedded engineers will have some experience with embedded machine learning in 2025. And I think these advanced tools around ML ops, where we enable engineers who don't necessarily have an ML background to do really solid work from everything through to from data collection through to deployment. These are going to become extremely important, and that's where all of these advances that we've talked about in the previous slide are going to be exposed to engineers. So there's some huge potential here. I think this is going to be an absolutely transformative technology. And I think if you're working in this space right now, this is going to be a really exciting next few years. So thank you so much for listening to my talk. If you'd like to know more about Edge Impulse, the product that we're building, you can head to edgeimpulse.com. The book I mentioned on tinyML is published by O'Reilly. I also would really encourage you to check out tinyml.org. So I believe we're also partnering with this session on hosting some of the content, but we have weekly and bi-weekly sessions on tinyml.org and on YouTube where you can see people who are at the leading edge of this field speak, and we'd love to have you as speakers too. If you want to chat with me or ask any questions, feel free to send an email, or you can find me on Twitter. But thank you so much, Stephen, for the invitation, and I hope this was a useful talk.
Thank you, Daniel. This was excellent. Thanks for putting the time together to come today and present. Really good to see what Edge Impulse is doing to enable this enormous ecosystem that's going to develop over the next few years, and is developing. And I think you're providing some excellent platforms to help it grow. And congrats on the book. I see it's available on Amazon. So for anybody shopping on Amazon Prime Day today, you can drop that into your basket as well. And it should help.
Steve, may I make one comment?
Sure.
I was just going to say that we used the book in our summer workforce development programs, and we married it with one of the Arduino boards. So we've done some work. Michael actually is developing some stuff on that too.
Yeah, and Mike Stanley has a book as well. So another plug for Mike if you see his link on his slides.